All right, guys, Chapter 18 is the first chapter in Unit 5 or Part 5. Part 5 is our first chapter on what's called inference. Inference is a whole section of the AP curriculum. You have collecting data, describing data, probability, and then inference. So we are on the last main topic. Units 5, 6, and 7, oops, that's not 6, 6 and 7 are all inference. So we are entering the downward slope of the end of the course. Chapter 18 is your base chapter for all understanding of the rest of the unit. So it's an important chapter, and it's all about something called the sampling distribution. The sampling distribution. So we're going to move into a couple of slides of this chapter tonight, and talk about something called the central limit theorem for sample proportions. So what I want you to do is refer to your Chapter 18 overview sheet, and make sure you understand the difference between proportions and means. We're starting this unit with proportions. This is the exact difference between categorical data and quantitative data. So here you see a bunch of information on proportions. And the whole first part of the chapter is proportions, and then the second part of the chapter is for means. So proportions are what we talk about when we're doing a categorical variable, like the color of M&Ms. It's the binomial model. I can count the number of M&Ms for the binomial model, which is what we just did, or how many people smoke or don't smoke, or how many people will vote for somebody in the next election. But if I take the number of people and that's the success, and then divide it by n, I'm creating a proportion. So the binomial model leads us straight into calculating a proportion. You just take the number of successes and divide it by n, and you have a proportion instead of the number of. Makes it relative to the total number of people. We use P for proportions. We use the actual letter P for a population proportion, for a model proportion, and we use P hat. We've seen Y hat, now we have P hat for a sample proportion. So if I were to draw a sample, let's say I get a bag of M&Ms. I buy a bag of M&Ms. I open the bag up. I count the number of red M&Ms and divide it by the total number of M&Ms in the bag. That's a P hat. That's in this sample, this is the proportion of M&Ms. But we probably know some general P. They probably make 10% of all M&Ms red. That's a population P versus this sample happened to have 12% red. That's a sample P. And what we're going to do is we're going to model what we think the sample P's should look like. That'll help me decide if this sample of 12%, is that unusual or is that usual? Of course, we're going to need a standard deviation to measure that. Hopefully you are picking up on these things. And so this whole first part is talking about proportions. Then we'll move into means in the same chapter. And then down here at the bottom, it's just the difference in words between the distribution of a sample and the sampling distribution. We've already done distributions of the sample. That's what we did in the first few chapters, where we took data, we made a histogram. But now, what if I want to look at the sampling distribution? And I'll talk what about that means in just a few minutes in the PowerPoint. But you can see some distinctions here. And this last sentence here is a really important sentence. When conditions are met, the sampling distribution turns out to be normal. We're going to talk about that today. Centered at the population mean or the population proportion with a set standard deviation that we're going to learn how to find. If we can use the normal model, then that allows us to do inference And inference is the whole last portion of this book, so you can imagine that it's fairly important. All right, moving into the PowerPoint. The central limit theorem for sample proportions, and I can show you a demonstration of this in class, an applet that shows you what the central limit theorem is telling you. All right, rather than showing real repeated samples, we're going to imagine what would happen if we were actually to draw many, many samples. First of all, remember we're dealing with proportions. Proportions are the number of successes divided by n. So this comes straight out of the binomial model. It's why it's next. Binomial measures the number of successes in a set number of trials. Now we're just going to divide by that total number of trials and get a proportion. So if I'm talking about my red M&Ms, I expect there to be 10% red M&Ms, so P would be 10. That's the proportion of success, 0.10, excuse me. Now, imagine what would happen if we looked at sample proportions for all these samples. So imagine you could actually draw every possible sample of a set size. It's impossible to truly do, but we can simulate it using computers and simulation. So that's where this is leading, and I can show you that simulation. But if you can imagine picking every single small bag of M&Ms in the world, opening them up and measuring all of the sample proportions of red, those would all be a bunch of p-hats. Sample proportions are p-hats. So maybe in one sample it was 12%, in another sample it was 10%, in another sample it was 9% red. We got a whole bunch of samples, and we would keep going. You need to do all of them. You have a whole bunch of sample proportions of red M&Ms. Now, imagine if we took all of those sample proportions and made a histogram of all of these sample proportions. This is called the sampling distribution of the proportion. A histogram of all of the sample proportions. So if we made a histogram of all the proportions from all possible samples, then what we're creating is the sampling distribution of the proportions. What do you think this histogram should look like? Moving on to the next slide, you'll see the answer, but I would hope you would at least imagine that it would be centered near the population proportion of 10%. If we truly believe 10% of all M&Ms are red, then all these samples should be near 10. That's your center. Should be near 10%. What about the shape and the spread? Let's talk about that. All right, just like I said, we would expect the histogram of the sample proportions to be centered at the true proportion, which is P, of the population. As far as the shape of the histograms to go, we can simulate a whole bunch of samples that we didn't really draw and then look at them. We can't do this in reality. We could do some in reality, but we can't do all of them in reality. So when we do simulation, it turns out that this histogram is roughly unimodal, symmetric, and centered at P, which leads us into the fact that this histogram can be modeled by the normal model. And that's a really awesome fact because that's what we use for the rest of the book, that we can use the normal model for all of these sample proportions, the distribution of the sampling distribution. Modeling how sample proportions vary from sample to sample. This is an important concept. We are modeling how the sample proportions, how all those p-hats vary from sample to sample. Kind of keep repeating that in your head. Is one of the most powerful ideas we'll see in this course. Remember opening all those different bags, finding all those different p-hats. They're not all going to be the exact same number. How do they vary is what we're looking at. That is the sampling distribution model. We are modeling how the proportions vary from sample to sample. We're going to quantify that variation. In other words, we're going to find the standard deviation. And then we're going to ask ourselves how likely it is that we observe a sample proportion in any particular interval. The normal model helps us do that. But if we're going to use the normal model, of course, there's two parameters for the normal model, the mean and the standard deviation. So those are the two things that we need to talk about right now. First off, the mean, mu, is P. P is the population proportion. It should make sense. It shouldn't be much memorization. However, it is on your formula sheet. I'll show you in just one second. So our mean is going to be P. Now let's talk about what the standard deviation is. When working with proportions, knowing the mean automatically gives you the standard deviation. As long as you know P and N, you can find the standard deviation by doing the square root of PQ divided by N. You math people, you might understand that this formula derives directly from the standard deviation of the binomial model, which was the square root of PQN. All we're doing now is dividing by N. And if you want to understand why that N ends up underneath the radical, I can show you that face to face. I'm not going to do that in the video. So, the distribution of the sample proportion is normal, centered at P, with a standard deviation of the square root of PQ divided by N. On your formula sheet, right underneath the binomial model, which was our last formulas, right here, if X is a binomial distribution, this was the formula that we don't ever use. This is the mean, this is the standard deviation of a binomial model. Right here moves us into the mean of P hat. P hat's your sample proportions. Is P the standard deviation of P hat, your sample proportions. That's how sample proportions vary from sample to sample to sample. Is the square root of P, 1 minus P, which is just Q. You can just think of that as Q, divided by N. So it's on your formula sheet. So, make a picture, make a picture, make a picture. Of course, we've heard that. If we're using a normal model, then we can draw the normal curve. It's centered at P, the population proportion, not the sample proportion, the population proportion. And then we would expect, 95% of all samples to fall within 2 standard deviations. We can use our normal probabilities and our normal CDFs and our likelihood questions. Is this unusual, not unusual, to answer questions about a sample proportion. So if I told you I opened a bag of M&Ms and it only had 5% red, is that unusual? Or if it had 20% red, is that unusual? So we, of course, we know the mean is 10, but we need to find that standard deviation and then look at the normal model to answer that question. Moving on, because we have a normal model, for example, we know that 95% of normally distributed valuables are within 2 standard deviations of the mean. That's kind of what I just said to you. So we shouldn't be surprised if 95% of various polls gave us results that were near the mean, but varied above and below. We expect 95% to be within 2 standard deviations. What we're talking about is sampling variability. You will sometimes hear this called sampling error. Don't get confused with error as being a negative word. That does not mean we did something wrong. It is not an error. It's just variability, variation that we expect from one sample to another. If one pollster conducts a poll of who they're going to vote for and they have 57% of people are going to vote for candidate A, and another poll says 59% are going to vote for candidate A, that doesn't necessarily mean one's right, one's wrong. They have different people in their sample. You expect sampling variability on that proportion. sampling variability, sometimes called sampling error, not necessarily an error, but rather variation from sample to sample. How good is the normal model? Well, in the binomial model, you learn that you can't always use the normal model. You do have certain conditions, and fortunately for us, those are just about the same. So, move on. We'll talk about the conditions and assumptions. All right. Most models are useful when specific assumptions are true. Don't forget, sometimes you're going to be told to assume normal model is okay. If you are told the normal model is okay, then you're good to go. You can move on. You don't need to go through any of this. But if you have to justify using the normal model, then you need to make sure you have independence, and you need to make sure the sample size is big enough. We have two conditions that we check for independence, two conditions that we check for independence. We'll go through those in 1 minute, and one condition that we check for sample size large enough. So we have three conditions that we're going to have to check to help us make our two assumptions. So assumptions are hard, often impossible to check. That's why we assume them. But you still need to have some sort of, reasonable idea if they are true. So those are the conditions that we're going to check. The conditions are randomization, 10%, success and failure. None of these should be new to you. We've already discussed about all of them. They're categorized in the next slide. Randomization, 10%, success and failure. The sample that you're looking at should be a random sample. It should be some sort of simple random sample of the population. If, they're not random, then they're related, then that P, that population proportion, may not hold true for this sample. It's not a good representation of the population. So we need randomization, and we also need the 10% condition, which is what we talked about last unit. The sample size must be no larger than 10% of the population. No larger means the same thing as less than or equal to 10% of the population. These first two conditions are the two conditions that help us assume independence. The first two help us assume independence. We should have independence between our samples. The third one is the sample large enough condition. This is how we decide if the sample is large enough. That's our 10% condition. It's the exact same condition we use for the binomial model. NP and NQ both need to be at least 10 or greater than 10. Some of you, I wrote on your quiz, did not actually calculate these two numbers or did not write this out in context. You do need to make sure that you find these numbers and write what they are in context. If all conditions are satisfied, then we can use the normal model. So a proportion is no longer just a single number computed from a set of data. It is now a random variable itself. The distribution of that variable, in other words, this bag had a p-hat, this bag had a p-hat, this bag had a p-hat, this bag had a p-hat. We have all of these p-hats that could potentially be any random number, although we expect it to be 0.1. The distribution of that is called the sampling distribution. Even though we depend on sampling distribution models, we never actually get to see them. It is actually impossible to take every possible sample from a population and make a histogram, but we can simulate it or we can imagine it. Computers have done it for us. We know if the sample sizes are large enough and all of our conditions are met, it will be roughly unimodal and symmetric, centered at P with a standard deviation of the square root of PQ divided by N. Sampling distribution models are important. This is an important sentence for me. This is something that I need you to wrap your brains around. They act as the bridge. from the real world of data, this real bag of M&Ms sitting in front of me with a certain p-hat, to the imaginary world of statistics, or the imaginary world of the population. We cannot actually count every red M&M in the world and see if the population is true, but we can look at this real world and ask questions about the population. I'm going to stop this video now and create a second video. We only have 2 more slides to get through. I've created a second video